Now we get to the first kind of vibration that we will study in a bit of detail, simple harmonic motion. This will be the first of 3 lectures on the chapter Simple Harmonic Motion, in which we will go over its definition and some of the different ways in which it can manifest. To define simple harmonic motion, one could say there are 2 main ways to go about it. For some function x of t that describes the motion of some object. Or if you want to be more general, which is not a bad thing at all, some other quantity, so not necessarily motion. One could, for example, define the motion explicitly. That is by saying it is simple harmonic if x of t is of some specified form. Or you could define it through a differential equation. That is by saying it is simple harmonic if x of t satisfies some specified differential equation. And depending on the textbook or other source that you use, you have a chance of encountering either or even another definition. A case could be made, I think, which I'll make later, that the differential equation approach is the better definition, but we'll get to that after we look at the explicit definition, which is a good introduction, where we can see what the form looks like mathematically and how to interpret it next to the motion itself. Then we'll move on to the differential equation approach, and the definition in terms of differential equation will be our official definition of simple harmonic motion. To define simple harmonic motion explicitly, let's look at the most tangible example of it. So in the early 1600s, as Galileo was tracking the position of the moons of Jupiter that he discovered in the night sky, such as Callisto in bottom left of the picture, he noticed that it had this kind of back and forth and back and forth and back and forth motion. The reason for that is simply because Callisto in its orbit represents approximately uniform circular motion, or movement around a circle at a uniform speed. Now, in your mind's eye, you can imagine what that would look like when viewed from the side, when your eyes are in the same plane as the circle. It's going to be this kind of back and forth motion, like this. Here Callisto is going around Jupiter, and as we start to look at it from the side, we get this kind of back and forth, and this is called simple harmonic motion, or at least an example of it. So this will be our approach to finding a formula for it. Let's see if we can derive an expression for 1 second. What we're seeing right now. What function describes this? So let's start by overlaying some axes and ask ourselves, what is it that we see if we were to stand here with our eyes in the same plane as the circle and looking at Callisto? Well, what we see is basically just Callisto's x-coordinate, or its shadow on the x-axis, or its projection on the x-axis, which will be different for every t value. So let's call that x of t. And how are we going to find x of t? Well, if we have the radius and we know what angle Callisto is making in this axis system for any t value, then we can easily find it. Suppose the radius is a and the angle for any t value is theta of t. Then x of t is simply a cosine theta of t. And if we have the rotation speed in radians per second, then we can write it in an even better form. A cosine of omega of t, where here we have also added the plus phi term, which is simply there because if it wasn't there, then when t is 0, in other words, if the bracket ended here and we did not have this, then when t is 0, x is a. That means that necessarily Callisto has to be here when t is 0, which is a completely unnecessary restraint given that we're after a general expression for this kind of motion. Callisto could be here, for example, when we start looking at t equal to 0, in which case pi would be 180 degrees, or rather pi radians, so the starting angles. Remember, we don't use actual degrees in the angles, so when we're talking about angles, we sometimes use degrees. Right, so now that we have a formula, let's see if we can reconcile it with the motion itself. So in both cases, the Callisto, or the red dot, will do one complete counterclockwise rotation. Only on the right-hand side, the starting angle is not at 0 degrees or 0 radians. But let's look at the left side first. Now we know what the formula is for x of t, so we know what it's going to look like. That's not the point. The point is that it should make sense to you that it does look that way. So trace it and replay it several times until it's obvious, so that you can understand why x of t is what it is relative to the motion above it. So let's play the animation. And then it go to minus a, and now it should go back to 0, and then finally back to a. Okay, so replay that several times until it makes perfect sense to you. And of course we can do the same on the right hand side, the only difference being that we've got a different starting angle. So essentially still the same thing, just shifted compared to the left hand side. Okay. Right, so now we can state our first definition of simple harmonic motion, the one mentioned earlier. It is simply motion for which the displacement function has this specific form, which we now know perfectly where it comes from. And the explanation of the terms a, omega, and phi are just constants, and we saw what they mean. A is the amplitude of the motion. Omega t plus phi, the angle given to cosine, that we call the phase of the motion. That is in radians. Omega is the angular frequency in radians per second, and phi is called the phase angle or phase constant. And now important a standard to keep in mind when you want to write down x of t for whatever situation, the amplitude is always taken as a positive value. Same thing for the angular frequency. There's no mathematical imperative to do it that way. It just makes it easier to immediately interpret and read the expression. So that is what we will do. We will always write a and omega as a positive value. Now you might object and say that, well, why should omega be positive? Couldn't it be negative? Relative to what we did before, negative omega might refer to clockwise rotation and not the counterclockwise kind that we saw, which is quite correct. But don't forget, we're not looking at uniform circular motions where it's going to be either clockwise or counterclockwise. No, we're looking at simple harmonic motion, the shadow of that kind of uniform circular motion, or the shadow of such kind of uniform circular motion is an example of simple harmonic motion. And there is no counterclockwise or clockwise in that. It is just moving from one side to the other side, the one side to the other side. So it doesn't matter. There's no clockwise or counterclockwise there. So we will always be able to describe that kind of motion for a positive choice of A and a positive choice of omega, provided we can choose the correct phase angle. Okay, but we'll see that in the later problems. Okay, so what's the period of this motion? Okay, now this is simply t equal to 2 pi over omega. And this is a formula that you don't have to memorize, you just have to know where it comes from. The more you understand, the less you have got to memorize. One complete cycle or one complete oscillation will be the time it takes for this term to go from 0 to 2 pi. So if that time is capital T, then it means that omega capital T is 2 pi. Or in other words, T is 2 pi over omega. All right. So I didn't remember this formula. I quickly I quickly reasoned what it has to be. So it's one less thing to remember. And the frequency, of course, is then just the inverse of that. Right, so now it's a very simple matter to find the velocity and acceleration functions. Given that x of t has that very basic form, we just have to very easily differentiate it once to get velocity or twice to get acceleration. And as for what those graphs look like, here is what you've seen already before, the displacement function x of t, importantly only for one oscillation, because I mean there are many oscillations. If there are several oscillations, then I mean the graph just keeps going, and the same for the other graphs, but we're only showing it for one oscillation. So they're the same. For one oscillation there's the velocity function, and for one oscillation the acceleration function. Now, similar to before, you have to be able to interpret these graphs relative to the motion itself. So if I play the motion, you should be able to see that these graphs make sense. For example, these peaks that represent when the dot is at the endpoints at A, minus A, and back to A, minus A, and back to A. There you can see that is where it's turning around. So in other words, you can see that is where the velocity is going to be 0. But as it's turning around, it's also experiencing its greatest acceleration, which is represented by these peaks. And here in the middle, it's moving at its fastest. See, it's going faster, faster, slower, 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 faster, 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 slower, slower, slower. Okay, so there it's at its fastest when x is 0, which is represented by these two peaks. And there's also no acceleration here, represented by these two intercepts. Okay, so it's important to be able to make sense of these graphs relative to the motion itself. So replay the video a couple of times until it's perfectly obvious. You can also very easily see what is the maximum velocity and maximum acceleration, just the velocity amplitude omega a and omega squared of a for the acceleration, maximum acceleration. Right, so exercise 1. We consider an object undergoing simple harmonic motion. It does 15 oscillations in 3.5 seconds. Its amplitude is 7 centimeters, 7.0 centimeters, and what is the object's maximum velocity? Right, so I know that its displacement or its motion can be described by this formula. And I'm given that A is 0.070 meters. Well, you can keep it centimeters, just keep track of the units and your answers will be in centimeters per second. But meter per second is more standard. Okay, and the velocity that we know, it's just a derivative, so that's minus omega a sine of omega t plus phi. And V max, maximum velocity, is in other words omega a. I have a, don't have omega. But what do I know? I know that the period is going to be 15 oscillations, or rather other way around, 3.5 seconds divided by 15. Takes that long to do this many oscillations, so this should be the time of one oscillation. And I know that the period is related to the angular frequency omega by 2 pi over omega. So 2 pi over omega is 3.5 seconds over 15. So omega therefore is equal to 30 pi over 3.5 seconds. Okay, good. So there I have everything. I forgot omega and I've got a. So now just substitute and calculate. 30 pi times, I messed up, equals 30 pi times 0.070 meters over 3.5 seconds, and that we can calculate. Don't make a mess like I am. Okay, so 30 times pi times 0.07 divided by 3.5. Good, this much. Well, I won't leave it like that because I can't provide exact answers here. That looks like a measured value to two significant figures. So I'm going to give an answer to two significant figures. So that is 1.9 meters per second. Okay, so now let's move on to the second way of defining simple harmonic motion. We say that the system for which the equation of motion satisfies this differential equation is one that is undergoing simple harmonic motion, where omega is some constant. This will be our formal definition, and the one that you and I are expected to use from now on to show that something is undergoing simple harmonic motion. Now, the obvious question to ask is, how does this relate to the first definition, where we gave a form of the function, which we called 1. The connection is simply that 1 is a solution of this differential equation, which you should go and check yourself. Moreover, and importantly, the formula that we gave there, the form that we gave in 1, is the general solution of this differential equation, meaning that all solutions of 2 are of this form. Now, the reason why this is a better definition, as we will see in a minute, once we get to some concrete examples, is because you're more likely to arrive at this differential equation first, from which you can then deduce that the solution of it is of this form. So chronologically, working through a problem, you should expect to naturally go from this to this, which is why this is a better definition. And also, the differential equation, as it's stated there, is more readily generalizable. Right, so exercise 2. We've got that the displacement function satisfies the given differential equation, and we're asked for the frequency of the oscillations. Okay, so let me rewrite that differential equation a little bit. So 16 times second derivative of y with respect to t squared plus 64 y is equal to 0. I divide by 16, then 64 divided by 16 is 4, that's 2 squared. So the second derivative y dt squared plus 4 is 2 squared y equal to 0. So thus, what is this? This is simple harmonic motion with angular frequency, and please don't abbreviate like this in your tests and exams. It's just for brevity for me. And so this is simple harmonic motion with angular frequency 2, well, omega equal to 2 radians per second. And we know that the period is 2 pi over omega. So frequency is omega over 2 pi, which so it's 2 over 2 pi. In other words, what is that? 1 over pi. So 1 divided by, okay, so 0.32 hertz. So 0.32 of an oscillation every second. Okay. Now for the concluding part of this lecture, we will look at various ways in which this differential equation can manifest itself. And hopefully start to make it a bit more clear why this kind of vibration is important. 1, it is perhaps surprisingly common, either directly describing the system or some part of it, or providing some approximation of it. And 2, as we will see with these examples, the settings are quite varied. I mean, we already looked at one setting, which was Callisto, and just, like a moon orbiting a planet. But the nature of the cases that we will now look at will be vastly different. Let's start by looking at perhaps the simplest case, or at least simplest next to the shadow of uniform circular motion that we started with. Just a normal block spring system like you are used to, where x of t is a displacement from equilibrium, and equilibrium meaning that there is no net force on the block. And we assume, to keep it simple, that the surface is frictionless, or at least that the friction is negligible. So perhaps it's just a very smooth surface with a thin oil layer, or the block is resting on an airbed, or it's a vertical arrangement where the block is hanging or suspended, and we choose to ignore air resistance. Either way, if we use Newton's second law, we get that mass times acceleration x direction is the force in x direction, so nothing funny there. We know that the acceleration is a second derivative with respect to time of the displacement, and Hooke's law, if we apply it to this force, as long as we don't stretch it out too much, the force should be approximately minus kx. And then if we rearrange that a little bit and notice that k and m are both positive constants, being the spring constant and the mass, I can write that k over m term as the square root of k over m squared. And you'll notice that is precisely the form of the simple harmonic motion differential equation, with omega being square root of k over m here. In other words, the angular frequency being square root of k over m. So I can tell from this that if there is disturbance from equilibrium, or I see this block moving about its equilibrium, oscillating about it, then it's doing so in a simple harmonic motion fashion with angular frequency given by square root of k over m radians per second. It should be clear from the preceding derivation that whenever we have got this kind of general setting, where some object can move in, say, x direction under the action of some net force, if that net force has that form, the same form from Hooke's law, minus kx for some k greater than 0, then the steps we followed in the derivation will be repeated. The exact same thing will happen. In the exact same way, we will arrive at the same simple harmonic motion differential equation. Which is why this is sometimes used as the definition of simple harmonic motion in some sources. And though it might seem like a very specific kind of thing, it's very specific or very specialized kind of property for a force to have, one can show that it's actually holds quite often, or at least it does to some close approximation. To make the case for this point, let's look at motion near equilibrium in very general terms. So we're going to consider an object that moves under the action of some conservative force, so like gravity for example, with a potential energy function given by V of x. Then the potential energy is defined as minus the integral from some reference point, 0 in this case, so it could be anything at all. We're free to choose this up to x and then fs ds. And thus, what do you get if you differentiate this? Hopefully you recognize this. This is precisely in the form of the first part of the fundamental theorem of calculus. The derivative for v of x here is just minus f of x. So definitely go and look up the fundamental theorem again and see that this is just a direct application of it. Now let's suppose that the object is at equilibrium somewhere, and we've chosen our coordinate system such that that occurs at x equal to 0. And furthermore, for convenience, let's choose a reference point for the potential energy so that the potential energy is 0 at 0. Okay, so in other words, we just take the equilibrium point as the 0 point or the reference point for the potential energy, which we are completely free to do. So thus the v of 0 is equal to 0 due to this convenient choice. And because it's equilibrium, the force is 0, so V's first derivative at the potential energy's first derivative at 0 is also 0. Now we're going to look at the Maclaurin-Taylor series of the potential energy about x equal to 0. And here we have we see the first three terms of it. Of course, there are extra terms. There is the x to the power 3 term and the x to the power 4 term and so on. You can refer back to first year calculus or your first year calculus textbook if you want to quickly read up on this again or revise it. Now in our case, this will simplify. As we saw on the preceding slide, the first two terms will fall away. So we end up with this, where this simply refers to all terms of order 3 and higher. So we can find in here x to the power 3 and x to the power 4 and higher. So no x squared or x's or any other constants in here. Now, this we can simplify even further, because we can simplify it even further if we move closer to equilibrium. And the point is we want to see what's going on if there's motion close to equilibrium, near to equilibrium. But equilibrium for us is at x equal to 0. So close to equilibrium means a small x value, and vice versa. And what will happen if the x values become small enough, it's going to eventually reach a point where these higher order terms become negligible. So for example, suppose you have an x squared term on one side, you have an x squared term, and you have something like a 10x to the power 3 term. Now if x is 1 over 10, then x squared and 10 times x to the power 3 are the same. But if you make x much smaller, so let's make x 1 over 1,000, let's say, not 1 over 10, but 1 over 1,000, then x squared becomes 1 over 1,000,000, and 10 times x to the power 3 becomes 1 over 100 million. So now the 10x to the power 3 term is smaller than the x squared term by a factor of 1 over 100. If that is still not a small enough difference for you, you can make x even smaller. Point is, if the x is small enough, close enough to 0, then the higher order terms will eventually reach a point, irrespective of the coefficients in front of them, that it will reach a point where those terms can be ignored to very close approximation. So then you will have this, from which it simply follows that the differentiate that the force is given by minus the second derivative of the potential energy at 0 times x. So if we define k to be equal to that constant, the second derivative of the potential energy at 0, and if that is greater than 0, then notice what happens. We get Hooke's law back. Or not back, we get it. Which we know will lead to the simple harmonic motion differential equation. So therefore, motion around the equilibrium point can be simple harmonic. However, it's only approximation. It's going to depend on how close to equilibrium you are. Because of the way we got here, we threw out a bunch of terms. So we had to throw out a bunch of terms, but we can only really do that if we're close enough to equilibrium. Suggesting that the simple harmonic motion approximates it can be used as an approximation for the real motion around the equilibrium point, but it's going to be a better approximation the closer to equilibrium you are. And notice we've been talking in very general terms, no mention of block springs or whatever. So in principle, this should hold in many different cases. Whenever you have some object or thing moving under the action of a conservative force, and for which there is some point where there's equilibrium, then in principle you can repeat these steps and arrive at Hooke's law again. I don't know why I say again. Not again, you can arrive at Hooke's law. So this is much more general than the block spring system that we looked at. We still have a little bit of a problem here. It's specifically when the second derivative of the potential energy at 0 is positive. I mean, it could be negative, it could be 0. So we might leave it at that, just if this is positive, then we can have simple harmonic motion, and then just leave it at that. But it's perhaps worth thinking about it a little bit and see if we can get some idea of what this might mean, or what kind of physical setup or circumstance this might correspond to. Now, because of the way potential energy is defined, this term being positive means that the force's derivative at 0 is negative. And if you think about this geometrically, I don't want to get into this too much without looking at actual graphs, which we'll look at in the next scenario. But if you think about this a little bit in your mind's eye, you can deduce that the derivative, or the slope of the graph, is therefore negative at the equilibrium point. So that would necessarily mean that the force goes from positive to negative, from left to right across the equilibrium point, if rightward is the positive direction, which in particular is the case for a restorative function, which if you disturb from the equilibrium position, the conservative force counteracts that and results in a force back towards the equilibrium position. Okay, but that's a little bit difficult to see in your mind's eye, so we'll try to look at a more tangible example to illustrate this, as well as the other ideas that we used in this motion near equilibrium analysis. So for the second to last example, let's look at interatomic forces. So this will be a particular instance of motion near equilibrium from the previous slides. So here the force function represents the general shape of the force functions for representing the force on an atom by its neighboring atoms, with the accompanying potential energy curve. And you can see here at gamma, the force is 0, so there we have an equilibrium point. Although we could also see it here because the slope is 0, so the force is 0 here at gamma. So that's again equilibrium point. Now, what is the atom physically going to do if it is here on the potential energy curve? In other words, if the R value, its position is at R equal to A. If additionally the total energy of the atom is H. Well, if the total energy of the atom is H and it is here, then the potential energy is H, so therefore the kinetic energy is 0. Okay, so now what's the atom going to do? It goes to the left or to the right? Well, it depends on the direction of the force. Is the force positive or negative? Well, I can see here to the left of gamma, the force is positive, so it will feel a force in the positive direction and it will move towards the right. Though I could also see it by arguing in terms of the derivative of the potential energy function. the force here is minus the slope of the potential energy function. So, and the slope here is negative. So negative times negative is positive. So the force is positive. So yeah, it's moving towards the right. So it'll move on the potential energy curve towards the right. Here the potential energy is 0. So it's at maximum kinetic energy. And then it continues moving until the potential energy is equal to the maximum H again as well. And so kinetic energy again is 0. And then for exactly the same reason, just reverse, it now moves back to A. So it will oscillate between A and B. And this will be approximately simple harmonic motion. The closer that H is to 0, or the lower the energy value of the atom, then clearly the closer the motion is to the equilibrium point, and the more accurate the simple harmonic motion approximation is. And also notice that relative to that condition that we added right at the end in the previous slide, we required the second derivative of the potential energy at the equilibrium point to be positive. Now, can you remember your calculus? Judging by this shape, is the second derivative for this portion positive or negative? So can you remember that from calculus? So for this kind of minimum, the second derivative is in fact positive. So very nice. Now it's important to realize that this guess here, we've got a pretty good idea from where this comes from, and how this ties into the analysis that we did on the previous page, in terms of, in the previous slides, in terms of the second derivative being positive and so on. So we've got a pretty good idea of where this comes from, but it's important to realize that we could have made this guess without the previous analysis. If you understand one thing, remember we said that if f is of the form f of x equal to minus kx, then that is simple harmonic motion. In particular, that would be simple harmonic motion around 0. If you want it around some other point like gamma here, you would have to have f of the form f of x equal to minus k, then in brackets x minus gamma. So in other words, a straight line through the equilibrium point with a negative slope. That directly gives you simple harmonic motion. That's straight up Hooke's law, simple harmonic motion. Now, we don't have a straight line here through the equilibrium point, but it should be clear that you could approximate this as a straight line with a negative slope through the equilibrium point. It's particularly if you zoom in very close. I mean, it's going to be indistinguishable from a straight line with a negative slope through the equilibrium point. So from that, it would be an intelligent guess to make that close enough, at least, to the equilibrium point, where the force function just looks like a straight line with a negative slope through the equilibrium point, we should have at least approximately simple harmonic motion. So we could have guessed this even without the previous analysis. But because of the previous analysis, we have a much better idea of why this is approximately simple harmonic around the equilibrium point. And if you were to calculate the actual frequencies in cases like this, you can get very high values from things of the order 10 to the power 13 hertz and figures in that range. For the final example, let's look at something completely different, LC circuits. You'd be forgiven to think that simple harmonic motion and that differential equation is restricted to the domain of actual physical things oscillating between points. Not the case at all, and this LC circuit perfectly illustrates it. So refer back to exercise 5 and 6 and see how we used Kirchhoff loop's rule to derive a differential equation. You should be able to essentially just copy and paste the relevant parts there to create this differential equation. And see what happens if I rearrange it a little bit. And remember here, Q represents the charge on the capacitor plates. Now this hopefully will look extremely familiar. That there is the differential equation for simple harmonic motion for the function Q, representing the charge at time t on the capacitor plates. So the charge Q is undergoing simple harmonic motion. This is quite extraordinary. What does this actually mean? It means that the charge on the capacitor plates will continuously flip from positive to negative and positive and so on. So in one half of an oscillation, this will become negative and that positive. by the same amount that it was, just reverse, and then half an oscillation further, it will be back to where it started. The same amount of charge, just flipped from positive, negative, negative, positive, positive, negative. And it will do so according to this function, and where the frequency, the angular frequency is given by omega, which in this case would be the square root of 1 over LC. So you can work from this you could easily calculate what the frequency is in hertz. So the current is going to continuously go clockwise and anti-clockwise and clockwise and anti-clockwise, reversing the charge on the capacitor at this angular frequency, from which you can calculate the normal frequency in hertz. And you can control what that frequency is very easily. You just need to control L and C. And that's easy to do. To control the capacitor's value, you change that by changing the surface, the parallel surface area and the distance between the plates. So then you can control the capacitance. And for the inductor, you can change that the easiest by just making more coils in the little turns of the wire. So both L and C are both inductance and the capacitance are things that are in principle easy to alter, and which means it's in principle easy to get a very specific frequency at which the current changes from clockwise to anticlockwise, clockwise to anticlockwise. And this is exploited in electronics a great deal. This is what it's called, I think it's a tank circuit. So you can Google that. It is used in many different places for a variety of different reasons. And we will look at this a little bit more as we continue in the course. But anyway, it just goes to show that yet again, we arrive at this differential equation. So, which is why we define simple harmonic motion in this way, because this kind of thing isn't exactly rare. Okay, so that is it for the first lecture.